I mean, so when I say a few of them, I mean there's going to be twisted Tom-isomorphisms and untwisted ones, and ones where the bundle's oriented. And so I was going to say the general idea is there should be some class in what should this be? HK? Yes. So the reduced kth homology of your Tom space with twisted coefficients. So again, this is going to be like Poincare duality. So when you go through a Tom isomorphism, it's going to twist or untwist the coefficients. So note that this is the same as the kth cohomology of the relative homology. Ooh, that's so really getting ahead of myself. Okay, so that we get such isomorphisms as, for example, okay, so how's best to write this? So let's say, where do I want to start? Do I want to start there? Okay. So maybe we start at the reduced cohomology of the Tom space. So this is cohomology, which, as I said, is the cohomology of the disk relative to the sphere. So then Tom isomorphism is going to say that if so this cohomology, so if I cup, this is why I didn't want to do cohomology. It's much easier to state in homology. Yeah, let's do that. Okay, so if I cap with this class, this is going to give an isomorphism to H star minus K. Yep. Of, so like as I say, it's now going to twist the coefficients. And then, so I guess now I'm going to use the tubular neighborhood theorem to say that, is this right? No. Something's wrong. Yes, something's wrong. Okay, so I think the Tom isomorphism actually takes it to the total space of the disk bundle. Yep, sorry. And then I'm going to use the tubular neighborhood theorem to say that I can embed the manifold as the manifold as the zero section. So this is going to give another map. Just the, I guess, where are we? Homology. So this is going to be the inverse of the induced isomorphism on homology. So this is going to be I star to the minus 1. So that's going to take us to H. Oh, okay, that makes more sense. Yeah, okay. Or okay. So or through this projection. Yeah, I'm just sort of thinking ahead of myself, I think. To the base space. So this was a manifold, yeah. So it's still got twisted coefficients. So we can get a load of other Tom isomorphisms. So for instance, from twisted coefficients goes to untwisted coefficients, and if you cup with the cohomology, you should be getting an isomorphism to the cohomology of the base space as well. So these are all completely analogous to this, and they're proved in similar ways, actually, with sort of, I guess, proving that Umkehr maps are the same as taking this Tom, Tom operation followed by pushing forward. So I'm going to be using Tom isomorphisms quite a lot. Okay, so now I've said a load of things about vector bundles. I'm going to try and persuade you that the right analog for CW complexes should be spherical fibrations. So obviously we can't take vector bundles over CW complexes because they don't have the manifold structure. But we can take fibrations. So definition. So let's say spherical K-1 fibration. So this is going to be, start dividing the board. So Sk-1 to, so this is the total space of the fibration, and I'm calling that P. So that's going to be some CW complex. So has what I'm going to define to be the disk bundle. So this is going to be dk dE. So I'm going to find dE to be the mapping cylinder of P. So whatever I do, it should agree on the level of vector bundles, but be more general. And then again, I'm going to say has Thom space. Cone of P. Of P, let's say. Okay, so I guess the remark is so we can define an orientation character for a spherical fibration. So obviously we can get one for X, but the point is we can get one for E in a sensible way that kind of means something geometrically about the fibration. But I'm not going to go into that because I want to get quite a lot of stuff done. Okay, so we can define an orientation character for the spherical fibration, and it all works out completely analogously to vector bundles. So the point is that we can take twisted coefficients, and we can get all the same Thom isomorphisms, and we get all the same Thom isomorphism theorems. So I guess we'll get some kind of Thom class of the spherical fibration. So it's now living in HK of the Thom, well, so they've reduced HK of the Thom space with twisted coefficients. So this is the point that we can define this thing. So this is going to be HK of DE twisted coefficients. What does that mean? Okay, so yeah, the idea I want to impress on you is this is a much more basic idea than a vector bundle, in that every vector bundle, I can reduce it to this. I can say, take the disk bundle, take the sphere bundle, and then this pops out. But I'm saying that the other way is not the case, which I will talk about in the later stages of the second half of the lecture. Oh, okay, yeah, so another remark that I want. So I want to keep defining all these properties of spherical fibrations that are similar to properties of vector bundles. So another one is Whitney sum. So Whitney sum still works. Obviously we're going to have to change the notion of what a Whitney sum is slightly. But it should be compatible with a vector bundle, right? So if we take a Whitney sum of two vector bundles and then take the sphere bundle, so for instance we've got two vector bundles, we take the Whitney sum and then we take the sphere bundle of that, we want that to be compatible with taking the sphere bundle of the first one, and then this is the Whitney sum for these things. So I think Andrew just uses this operation still, but I found that a little confusing. So this is the fiber sum of two fiber bundles. So again, I'm not going to go into details of that really in Andrew's book, but this is the main point of the property, is that it works in the same way as Whitney sum if you pass back up the vector bundles. So this is the fiber-wise join. I really want to talk about that now. Oh, yeah, I thought I wanted to talk about something else. Okay. Okay. So then the point is, again, like with vector bundles, we can define a classifying space. So let GK be the monoid of homotopy equivalences from k-1 sphere, so it's going to be homotopy, to k-1 sphere. So it turns out that this is the correct thing to look at for the classifying space of spherical k-1 fibrations. So so any monoid has an associated classifying space.